Welcome to Sleepless Astronomer, where we explore the wonders of space and the universe. If you're enjoying these cosmic journeys, please like this video and subscribe to the channel. We post new videos every single day, so you can tune in whenever you want to learn about the cosmos. And we'd love to hear from you in the comments. Let us know where in the world you're watching from. We always enjoy connecting with fellow space enthusiasts around the globe. Now let's begin tonight's journey through the universe. The extreme environments where life could thrive. Life on Earth exists in places that seem utterly hostile to survival. In boiling hot springs where water approaches its boiling point, in frozen Antarctic lakes where temperatures remain below zero year-round, in crushing depths of the ocean where pressure would flatten most organisms instantly, in intensely acidic pools that would dissolve metal, and in radioactive waste sites where radiation levels would kill a human in hours. These extreme environments, once thought to be sterile and lifeless, actually teem with organisms called extremophiles, life forms that not only survive but thrive in conditions that would destroy most familiar creatures. Understanding where these extremophiles live and how they manage to exist in such harsh conditions reveals that life's possibilities extend far beyond the comfortable, temperate zones we associate with habitability, suggesting that alien life might flourish in environments throughout the universe that we would never have considered searching. Temperature extremes represent one of the most dramatic challenges for life. At Yellowstone National Park and similar geothermal areas worldwide, hot springs reach temperatures near or even above the boiling point of water. In these scalding pools, organisms called thermophiles and hyperthermophiles thrive at temperatures that would cook most life forms. Some bacteria live comfortably at temperatures around 180 degrees Fahrenheit, and certain archaea, single-celled organisms distinct from bacteria, can survive and reproduce at temperatures exceeding 230 degrees Fahrenheit in superheated water under pressure that prevents it from boiling. These heat-loving organisms have specialized proteins that maintain their structure at high temperatures instead of denaturing and unfolding like normal proteins would. Their cell membranes contain special lipids that remain fluid and functional at temperatures where ordinary membranes would fall apart. Their DNA includes protective mechanisms that prevent the double helix from separating under thermal stress. Every aspect of their biochemistry has been optimized through evolution to function at temperatures that would destroy conventional life in seconds. The existence of thermophiles suggests that life could exist in hot environments throughout the solar system and beyond. In volcanic hot springs on Mars, in heated cracks near lava flows on Jupiter's moon Io, or in the scalding oceans of planets closer to their stars than Earth is to the Sun. At the opposite extreme, psychrophiles, cold-loving organisms, thrive at temperatures well below the freezing point of pure water. In Antarctica, microbes live in lakes that remain liquid beneath ice, because salt lowers the freezing point, maintaining temperatures around -5 to -20 degrees Fahrenheit. These organisms produce antifreeze proteins that prevent ice crystals from forming inside their cells, manufacture enzymes that remain flexible and functional at temperatures where normal enzymes become rigid and useless, and slow their metabolisms to conserve energy in the cold. Some bacteria found in permafrost remain viable after being frozen for hundreds of thousands of years, suggesting remarkable cold tolerance. The discovery of psychrophiles revolutionized thinking about where life could exist in the solar system. Europa, Jupiter's ice-covered moon, has a liquid ocean beneath miles of surface ice, kept liquid by tidal heating from Jupiter's gravity. The water at the bottom of this ocean, near Europa's rocky core, might be relatively warm, perhaps just above freezing, and could host psychrophilic life adapted to darkness and cold. Enceladus, Saturn's small moon, shoots geysers of liquid water through cracks in its ice shell, water that comes from a subsurface ocean. Despite the frigid surface temperature of -330 degrees Fahrenheit, the ocean beneath remains liquid, warmed by tidal forces. Life in these hidden oceans would need to tolerate extreme cold, total darkness, and high pressure, but Earth's psychrophiles prove that temperature alone doesn't preclude life. Pressure creates another extreme that life has conquered remarkably. In the Mariana Trench, the deepest part of Earth's oceans, pressure reaches about 16,000 pounds per square inch, more than 1,000 times atmospheric pressure at sea level. This crushing pressure would compress gases, alter protein structures, and collapse air-filled spaces in ordinary organisms. Yet the trench is inhabited by fish, amphipods, bacteria, and other creatures specifically adapted to extreme pressure. These organisms have no air-filled swim bladders that would collapse. Their proteins are stabilized by special amino acid sequences and by molecules called piezolites that counteract pressure's effects on molecular structure. Their cell membranes contain unsaturated fatty acids that remain fluid under pressure instead of becoming rigid. The existence of Baraful's pressure-loving organisms suggests that life could exist in the high-pressure environments found deep within planets and moons. The subsurface oceans of Europa and Enceladus experience significant pressure from the weight of overlying ice. The deeper regions of these oceans, near the rocky seafloor, would experience pressures far exceeding anything at Earth's surface. Yet if Earth organisms can adapt to pressures in the Mariana Trench, alien organisms might adapt to even higher pressures in alien oceans. Some scientists even speculate about life existing in the liquid metallic hydrogen regions deep within gas giants like Jupiter, though the extreme temperatures and pressures there would require biochemistry completely unlike anything on Earth. Acidity represents another extreme environment where life flourishes. Highly acidic environments with pH levels below 3, comparable to battery acid or stomach acid, would dissolve most biological molecules and disrupt normal cellular processes. Yet acidophiles thrive in such conditions. Iron Mountain in California hosts drainage from abandoned mines with pH levels below 0, more acidic than concentrated sulfuric acid. Despite this extreme acidity, bacteria and archaea live in these toxic streams, deriving energy from oxidizing iron and sulfur. These organisms maintain neutral pH inside their cells while existing in incredibly acidic environments, pumping protons out of their cells faster than the acidic environment can push them in, a process that requires substantial energy but allows survival in places nothing else can tolerate. At the opposite extreme, alkalophiles live in highly alkaline environments, with pH levels above 9 or even above 11. Soda lakes like Mono Lake in California and Lake Magadi in Kenya have pH levels around 10, nearly as caustic as bleach. Microorganisms in these lakes have adapted to maintain their internal chemistry despite the harsh external conditions, using specialized proteins and transport mechanisms to survive. The existence of life in both extremely acidic and extremely alkaline environments suggests that pH is a challenge life can overcome through evolution, expanding the range of potentially habitable environments to include caustic lakes and springs on other worlds. Salinity creates osmotic stress that would kill most organisms. Normal cells placed in very salty water lose water through osmosis and shrivel up. Yet halophiles, salt-loving organisms, thrive in hypersaline environments like the Dead Sea, where salt concentration exceeds 30%, and in salt evaporation ponds where salt approaches saturation. Some archaea not only tolerate but require high salt concentrations to survive. They accumulate potassium and other ions inside their cells to balance the external salt concentration, preventing osmotic water loss. Their proteins are specifically adapted to function in high salt conditions and would actually denature and unfold in normal salt concentrations. Hypersaline environments might exist on Mars, where briny water could remain liquid at temperatures below the freezing point of pure water. Salts detected on Mars's surface could create localized regions where salty water exists seasonally or sporadically. If life ever existed on Mars, or if it exists there today, it might persist in these briny environments, sheltered from the planet's coal-thin atmosphere by adaptation similar to Earth's halophiles. Radiation represents one of the most challenging extremes. Ionizing radiation damages DNA, breaks apart molecules, and creates reactive free radicals that wreak havoc on cellular chemistry. Yet radio-resistant organisms can survive radiation doses thousands of times higher than would be lethal to humans. The bacterium Deinococcus radiodurans can withstand radiation exposure of several million rads, enough to shatter its DNA into hundreds of fragments and completely repair its genome within hours, reconstituting functional chromosomes from the pieces. This organism accumulates high concentrations of manganese compounds that protect its cellular machinery from radiation damage and possesses redundant copies of its genome, along with extraordinarily efficient DNA repair mechanisms. The discovery of radio-resistant life expands possibilities for life in high radiation environments throughout the universe. Mars's surface experiences high radiation levels because Mars lacks a strong magnetic field and thick atmosphere to shield the surface from cosmic rays and solar radiation. Any surface life on Mars would need radiation resistance. The moons of Jupiter, particularly Europa, exist within Jupiter's powerful radiation belts and experience intense radiation bombardment. Life in Europa's subsurface ocean would be shielded by miles of ice, but any organism near the surface would need extreme radiation tolerance. Desiccation, extreme dryness, challenges life by removing the water necessary for biochemical reactions. Yet xerophiles can survive in nearly waterless environments. Microorganisms have been found in the driest deserts on Earth, in salt crystals, and even in the upper atmosphere. Some organisms, like tardigrades, microscopic animals also called water bears, can enter a state called cryptobiosis when they dry out. In this state, they replace water in their cells with protective molecules like trehalose sugar, essentially turning into a glass-like solid that can survive for years or decades without water, then rehydrate and resume normal activity when water becomes available again. The ability to survive desiccation suggests that life could persist in extremely dry environments like Mars, where liquid water is rare and exists only transiently. Organisms in a cryptobiotic state could wait through long dry periods, potentially centuries or longer, then reactivate during brief periods when liquid water appears. This strategy might allow life to survive, even on worlds where habitable conditions are rare and sporadic rather than continuous. Oligotrophs thrive in nutrient-poor environments where most life would starve. These organisms can extract energy and nutrients from resources that seem impossibly limited. Some bacteria derive energy from oxidizing trace amounts of hydrogen gas or from reducing tiny concentrations of metal ions. Others grow incredibly slowly, dividing perhaps once per century or even less frequently, living at the absolute minimum energy budget that can sustain life. These organisms survive in deep subsurface rocks, in ultra-pure cave water, and in nutrient-depleted ocean regions. The existence of oligotrophs suggests that life could persist in environments throughout the universe that seem too resource-poor to support metabolism. Deep beneath the surfaces of planets and moons, in the pores between rock grains, organisms might eke out existence on trace amounts of hydrogen from water-rock reactions, or on the minimal nutrients leached from minerals over geological timescales. This greatly expands the potential volume of habitable space, not just surfaces and oceans, but the entire crustal volume of rocky worlds down to depths where temperature becomes prohibitive. Some of the most extreme environments on Earth combine multiple stresses. Hydrothermal vents on the ocean floor experience high temperature, high pressure, high concentrations of toxic metals and sulfur compounds, and complete darkness. Yet these vents support thriving ecosystems based on chemosynthetic bacteria that extract energy from chemicals spewing from the vents. Hot acidic springs combine high temperature with extremely low pH. Ice-covered Antarctic lakes combine extreme cold with high salinity and seasonal or permanent darkness. Life found in these multi-stress environments proves that organisms can adapt to simultaneous challenges, not just single extremes. This ability to tolerate multiple stresses simultaneously is crucial for evaluating habitability on alien worlds, where conditions often involve several challenges at once. Europa's ocean experiences cold, pressure, darkness, and possibly high salinity, all at the same time. Mars's surface experiences extreme cold, desiccation, high radiation, and low pressure simultaneously. Venus's clouds experience high acidity, moderate temperature, and the presence of sulfuric acid droplets. Each of these environments might seem impossibly hostile when considered as a whole, but examining them as combinations of specific stresses that Earth organisms have individually overcome makes them seem more potentially habitable. The extremophiles of Earth demonstrate that life is far more flexible and resilient than once thought. Organisms have evolved mechanisms to survive and thrive in virtually every environment on Earth where liquid water exists, at least transiently, and where some source of chemical energy is available. Temperature, pressure, acidity, salinity, radiation, desiccation, each extreme that seems to represent an absolute barrier to life, turns out to be merely another challenge that evolution can overcome, given time and the right selection pressures. These discoveries transform our search for life beyond Earth. Rather than looking only for planets with Earth-like conditions, moderate temperature, neutral pH, low radiation, abundant water, we can expand our search to include extreme environments throughout the solar system and beyond. Volcanic hot springs on Mars or Venus, frozen oceans on icy moons, the clouds of Venus, subsurface aquifers deep within asteroids, the hydrothermal systems that might exist beneath the surfaces of large moons. All of these become potential habitats once we recognize that life on Earth already thrives in analogous extremes. The extreme environments where life could thrive extend from the scalding vents of volcanic springs to the frozen lakes of Antarctica, from the crushing depths of ocean trenches to the desiccated rocks of the driest deserts, from intensely acidic mine drainage to alkaline soda lakes, from the radiation-blasted rocks near nuclear waste to the nutrient-depleted waters of remote caves. Each extreme habitat on Earth hosts specialized organisms that have turned hostile conditions into homes through remarkable biochemical and physiological adaptations, proving that life's potential territory extends far beyond the comfortable middle ground to encompass nearly anywhere liquid exists, energy flows, and raw materials can be found, vastly expanding the cosmic real estate where life might emerge and flourish across the universe. The powerful magnetic fields of dead stars. When a massive star exhausts its nuclear fuel and explodes as a supernova, the collapsing core is compressed into an object of almost incomprehensible density. A neutron star, containing more mass than the Sun, packed into a sphere only about 20 kilometers across. This violent compression doesn't just create extreme density, it also amplifies the star's magnetic field to strengths that dwarf anything found elsewhere in nature. The magnetic fields of neutron stars are among the strongest in the universe, billions or even trillions of times more powerful than Earth's magnetic field, strong enough to distort atoms, affect the fabric of empty space itself, and dominate the physics of everything near these stellar remnants. To understand how neutron stars develop such powerful magnetic fields, we need to consider what happens during the collapse. Before the supernova, the massive star had a magnetic field similar in strength to the Sun's, a few Gauss at the surface, comparable to a modest laboratory magnet. The star's magnetic field was generated by convection and rotation in its interior, creating currents of electrically conducting plasma that produced magnetism through the same basic dynamo process that generates Earth's magnetic field. When the star's core collapses, it shrinks from a radius of thousands of kilometers down to only about 10 or 12 kilometers, a compression factor of more than 1,000. As the core collapses, magnetic field lines are squeezed together. The strength of a magnetic field is proportional to the density of field lines passing through a given area, so compressing the core concentrates the field lines, amplifying the magnetic field strength enormously. The exact amplification depends on the details of the collapse, but conservation of magnetic flux, a fundamental principle stating that magnetic field lines cannot be created or destroyed, only moved around, requires that the field strength increase roughly in proportion to the decrease in the star's cross-sectional area. Shrinking the radius by a factor of 1,000 increases the magnetic field by about 1,000,000 times. A star with an initial field of 1 Gauss would emerge from collapse as a neutron star with a field of roughly 1,000,000 Gauss, or 1,000 Tesla. This is just the starting point. Most neutron stars have magnetic fields measured in hundreds of millions to trillions of Gauss. Earth's magnetic field, for comparison, measures about half a Gauss at the surface. The strongest continuous magnetic fields produced in laboratories reach around 45 Tesla, or about 500,000 Gauss, requiring enormous electromagnets and tremendous amounts of power. Yet neutron stars casually exceed these laboratory records by factors of millions or billions through nothing more than gravitational compression. Rotation adds another layer of complexity. The collapsing core spins faster as it shrinks, just as a figure skater spins faster when pulling their arms inward. Another consequence of conservation of angular momentum. A star that initially rotated once every few weeks might emerge from collapse rotating several times per second, or even hundreds of times per second. This rapid rotation, combined with the intense magnetic field, creates the phenomenon we observe as pulsars. A pulsar is a rotating neutron star whose magnetic axis is tilted relative to its rotation axis, similar to how Earth's magnetic poles don't align perfectly with the geographic poles. Charged particles near the neutron star's surface are accelerated along the magnetic field lines toward the magnetic poles, where they emit beams of radio waves, X-rays, and sometimes even gamma rays. As the neutron star rotates, these beams sweep through space like lighthouse beams. When one of the beams happens to point toward Earth, we detect a pulse of radiation. The pulses arrive with extraordinary regularity. Some pulsars keep time more accurately than the best atomic clocks over short timescales. The Crab pulsar, formed in the supernova observed in the year 1054, rotates 30 times per second and has a magnetic field estimated at around 1 trillion Gauss. This field is strong enough to do remarkable things. If you could somehow place a human body in such a field, ignoring for the moment all the other ways a neutron star would kill you, the magnetic field would be strong enough to distort your atoms. The field would force electrons into different orbital configurations, changing the chemical properties of matter and making normal biological chemistry impossible. But some neutron stars have magnetic fields even more powerful than typical pulsars. These objects, called magnetars, possess the strongest magnetic fields known in the universe, reaching 10 to the 15th Gauss, or 1,000,000,000 Tesla. These fields are so strong that they affect empty space itself. According to quantum electrodynamics, the quantum field theory describing how light and matter interact, extremely strong magnetic fields can cause the vacuum to behave in strange ways. The vacuum can become birefringent, splitting light into two beams with different polarizations, similar to how certain crystals split light. Virtual particle pairs, electrons and positrons that normally pop briefly into existence and then annihilate, can be affected by the field, altering how light propagates through the vacuum. In magnetar fields, atoms are stretched into elongated shapes, becoming needle-like structures rather than the familiar spherical electron clouds. The magnetic field overwhelms the electric forces that normally determine atomic structure, forcing electrons into highly unusual quantum states. Matter at the surface of a magnetar exists in forms never encountered anywhere else, with properties unlike any material found on Earth or in laboratory experiments. Magnetars reveal their presence through sudden outbursts of X-rays and gamma rays. The magnetic field stores enormous amounts of energy. In the strongest magnetars, the magnetic energy exceeds the binding energy holding the neutron star together, creating immense internal stresses. The neutron star's crust, composed of crystallized nuclear matter, occasionally cracks under these stresses in events called starquakes. When the crust suddenly shifts, the magnetic field lines snap and reconnect violently, releasing tremendous bursts of energy in seconds or less. The most powerful magnetar flare ever observed occurred in December 2004 from a magnetar designated SGR 1806-20, located about 50,000 light-years from Earth. In 1/10 of a second, this flare released more energy than the Sun emits in 150,000 years. The radiation from this event saturated detectors on satellites throughout the solar system and measurably affected Earth's ionosphere, despite the enormous distance. If this magnetar had been located only 10 light-years from Earth instead of 50,000 light-years away, the flare would have caused a mass extinction, stripping away the ozone layer and exposing the surface to lethal radiation. The origin of magnetar fields remains somewhat mysterious. The simple compression of the collapsing star's field cannot account for fields this strong. Magnetar fields are hundreds to thousands of times stronger than what compression alone would produce. Several theories attempt to explain the enhancement. One possibility involves a dynamo mechanism operating in the first few seconds after the neutron star forms, when the core is still extremely hot and turbulent. Convection in the proto-neutron star, combined with rapid rotation, might amplify the magnetic field through a dynamo process, similar to how Earth generates its field, but operating under extreme conditions for a brief time. Another possibility involves the formation mechanism itself. If the collapsing core rotates very rapidly, near the maximum possible rate, differential rotation between the inner and outer parts of the core might stretch and amplify magnetic field lines, winding them up like a spring and creating the immensely powerful fields observed in magnetars. This would suggest that magnetars are born from progenitor stars that were rotating particularly rapidly before collapse, or from binary star systems where mass transfer spun up the star before the supernova. The magnetic fields of neutron stars gradually decay over time. The field energy is dissipated through various processes, including emission of electromagnetic radiation and heating of the neutron star's interior. Typical pulsars with fields around 1 trillion Gauss might maintain those field strengths for millions of years. Magnetar fields, being much stronger, decay more quickly, possibly over tens of thousands of years. As magnetars age and their fields weaken, they might become ordinary pulsars indistinguishable from neutron stars that never had magnetar strength fields. This decay helps explain why magnetars are relatively rare. Astronomers have identified only about 30 confirmed magnetars in our galaxy, compared to thousands of ordinary pulsars. If magnetar fields decay on timescales of 10,000 to 100,000 years, and they form perhaps once every few hundred years in our galaxy, then at any given time, only a few dozen active magnetars would exist, which matches observations well. The magnetic fields don't just affect the neutron star itself, they extend outward into space, creating a magnetosphere. Charged particles near the neutron star cannot cross magnetic field lines easily, so they become trapped, spiraling along the field lines. The field forces these particles to co-rotate with the neutron star out to a distance called the light cylinder, where the co-rotation velocity would equal the speed of light if the field could enforce it. Beyond the light cylinder, particles can escape along the field lines, carrying energy and angular momentum away from the neutron star. This energy loss causes pulsars to gradually slow down. The Crab pulsar's rotation period increases by about 38 nanoseconds per day, as it loses rotational energy to the magnetic field and the wind of particles it drives. The rate of slowdown reveals how much energy the pulsar is radiating. Young pulsars with strong magnetic fields slow down quickly. Old pulsars with weaker fields slow down more gradually. By measuring both the rotation period and the slowdown rate, astronomers can estimate a pulsar's age and magnetic field strength. Some of the fastest spinning pulsars, called millisecond pulsars because they rotate hundreds of times per second, have much weaker magnetic fields than typical pulsars. These objects were spun up to high speeds by accreting matter from a companion star in a binary system. The infalling matter transferred angular momentum to the neutron star, spinning it up, while simultaneously burying the magnetic field under a layer of accreted material, weakening the external field. These recycled pulsars have been rejuvenated by mass transfer, given a second life as rapidly spinning objects with relatively weak fields. The study of neutron star magnetic fields connects to fundamental physics in several ways. These fields exist at strengths where quantum electrodynamics predicts effects that cannot be tested in any laboratory. Observations of magnetars and the radiation they emit provide the only way to study matter and vacuum behavior in such extreme magnetic environments. The fields also affect how nuclear matter behaves at the neutron star surface and in the crust, influencing the equation of state, the relationship between pressure and density of matter at nuclear densities and beyond. Binary systems containing two neutron stars allow even more exotic magnetic interactions. When two magnetized neutron stars orbit close together, their magnetic fields can interact, possibly reconnecting and releasing energy. As the neutron stars spiral together, driven by gravitational wave emission, the magnetic fields might play a role in the final moments before merger, potentially affecting the gravitational wave signal and the electromagnetic radiation emitted during the kilonova that follows. The powerful magnetic fields of dead stars represent nature operating at extremes impossible to recreate artificially, fields where quantum effects modify the behavior of empty space, where atoms are distorted beyond recognition, and where enough energy is stored to power the sun for millennia, all concentrated in objects small enough to fit inside a city, yet massive enough to contain more matter than an entire star. Fields that define the physics of these remarkable objects and make them among the most extreme environments existing anywhere in the cosmos. What alien civilizations might actually look like? When most people imagine alien civilizations, they picture humanoid beings with large heads, slender bodies, and advanced technology that allows them to cross the vast distances between stars. Science fiction has given us countless variations: green-skinned Martians, insectoid hive minds, crystalline energy beings, peaceful explorers, and hostile invaders alike. But what would alien civilizations actually look like if we base our expectations on biology, physics, chemistry, and evolutionary principles rather than imagination alone? The answer reveals possibilities both familiar and utterly strange, shaped by the same fundamental laws that govern life on Earth, but expressed through the infinite variations that different worlds and evolutionary histories would create. The foundation of any alien civilization begins with evolution. On Earth, Every organism exists because its ancestors survived and reproduced more successfully than competitors. Natural selection shaped everything from bacterial flagella to human brains, optimizing organisms for their specific environments and challenges. The same process would operate on any world where life exists. Alien organisms would be shaped by their planet's gravity, atmosphere, temperature, available nutrients, predators, and countless other factors operating over millions or billions of years. Evolution is relentless, creative, and opportunistic, finding solutions to survival challenges through whatever mechanisms work. Gravity would profoundly influence alien body structures. On a high-gravity planet, perhaps 1.5 times Earth's gravity, organisms would need stronger skeletal structures to support their weight. Animals might evolve shorter, stockier bodies with thicker bones and more powerful muscles. Tall, slender forms would be disadvantageous because they would require too much structural support and energy to maintain. Intelligent beings on such a world might stand only 3 or 4 feet tall despite being as massive as humans, with powerful legs and low centers of gravity to move efficiently under the stronger gravitational pull. On a low-gravity planet, the opposite constraints would apply. With less gravitational force to overcome, organisms could grow taller and more delicate. Bones could be lighter and more slender. Flying might be easier, allowing evolution to produce larger flying organisms than Earth's giant pterosaurs. Intelligent beings might stand 8 or 10 feet tall with elongated limbs, moving with a grace that would seem almost balletic to Earth-based observers. Their skeletal structure might resemble bird bones, hollow and reinforced with internal struts rather than solid like mammalian bones. The atmospheric composition would shape how aliens breathe and what biochemistry they use. On Earth, most complex life uses oxygen for metabolism because burning fuel with oxygen releases large amounts of energy efficiently. But oxygen was not always abundant. Early Earth had an atmosphere dominated by nitrogen, carbon dioxide, methane, and other gases. The oxygen we breathe today came from photosynthetic bacteria that gradually transformed the atmosphere over billions of years in what's called the Great Oxidation Event. An alien planet might never undergo such a transformation, leaving its atmosphere oxygen poor. Life there might use different metabolic pathways, perhaps based on sulfur compounds, hydrogen, or methane. The type of star a planet orbits would influence alien vision and perhaps their entire sensory experience of reality. Our sun emits most strongly in visible light wavelengths, the colours we can see, and Earth's organisms evolved eyes sensitive to these wavelengths because that's where the most light was available. But a planet orbiting a red dwarf star would receive most of its light in infrared wavelengths. Organisms evolving there might develop eyes sensitive to infrared rather than visible light. To them, what we call visible light might be invisible ultraviolet, and their daylight would be our infrared. An alien from such a world would perceive colours and see objects in ways completely foreign to human experience. Conversely, a planet orbiting a hotter, bluer star would receive more ultraviolet light. Evolution might produce eyes sensitive to ultraviolet wavelengths, allowing these aliens to see patterns and colours invisible to humans. Many Earth organisms, including bees and some birds, can already see into the ultraviolet range, perceiving patterns on flowers and plumage that humans cannot detect without special cameras. An alien species with full ultraviolet vision would experience a visual world enriched with information and beauty we cannot access. Communication methods would evolve based on environmental constraints and available sensory channels. On Earth, humans primarily communicate through sound, speaking and hearing, supplemented by visual cues like facial expressions and gestures. But sound travels poorly in thin atmospheres and not at all in vacuum. An alien species on a world with a thin atmosphere might rely more heavily on visual communication, color changes, bioluminescent patterns, or elaborate gestural languages. Octopuses on Earth already use color-changing skin cells, called chromatophores, to communicate, creating flowing patterns across their bodies. An intelligent species with similar abilities might communicate through rapidly shifting color displays, conveying complex ideas through patterns that flow across their skin in what would appear to us as living art. Some aliens might communicate through vibrations transmitted through the ground or through their planet's oceans. Whales and elephants on Earth use low-frequency sounds that travel great distances. Elephant calls can travel several miles through the ground. An intelligent species might evolve specialized organs for creating and detecting vibrations, communicating through seismic signals that travel through rock or sediment. Their language would be invisible and inaudible to humans without special equipment to detect the vibrations. Chemical communication, already used extensively by Earth's insects through pheromones, might become the primary communication method for some species. Aliens might communicate through releasing complex mixtures of chemicals that other members of their species detect through sensitive chemoreceptors. Their language would consist of scents and tastes, with grammar and syntax encoded in the ratios and combinations of different molecules. To humans, their most profound poetry and scientific papers would be nothing more than smells. Body structure would reflect evolutionary history and environmental pressures. The bilateral symmetry seen in most Earth animals, a left side mirroring a right side, emerged early in evolution and became locked in. But aliens might evolve radial symmetry, like starfish, with body parts arranged around a central axis. An intelligent being with radial symmetry might have arms, eyes, and sensory organs distributed evenly around their body, giving them a 360-degree field of awareness with no natural front or back. Their psychology and culture might be profoundly affected by experiencing the world without a preferred direction of travel or attention. The number of limbs is not fixed by any physical law. Earth's vertebrates settled on 4 limbs relatively early in evolutionary history, but arthropods, insects, spiders, crustaceans have 6, 8, or even dozens of legs. An alien species might evolve with 3 limbs arranged in a triangle, giving them stable tripod support at all times. They might have 6 limbs, 4 for walking and 2 manipulator arms. Or they might have dozens of tentacles like an octopus, each capable of independent complex movement and manipulation. Their tool use and technology would develop along entirely different lines than human technology, shaped by their different manipulative abilities. Intelligence itself might manifest in forms unlike human intelligence. Human intelligence is highly centralized. Most of our cognitive processing occurs in our brain, a single organ in our head. But octopuses, among Earth's most intelligent invertebrates, have a distributed nervous system with neurons throughout their arms that can make independent decisions. An alien species might have multiple brain centers distributed throughout their body, or they might have a collective intelligence where individual organisms are relatively simple, but groups display emergent intelligence through their interactions, similar to how ant colonies solve complex problems that individual ants cannot. Social structure would influence civilization development. Humans are intensely social primates who naturally form groups, cooperate, compete, and create complex hierarchies. An intelligent species that evolved from solitary predators might have very different social instincts, perhaps coming together only to mate and raise young, then separating again. Their civilization would be built by individuals who value isolation and independence over community and cooperation. Or aliens might be eusocial, like bees or ants, with specialized castes, workers, soldiers, reproducers, genetically programmed for different roles. Their civilization might function as a superorganism where individual identity barely exists. Lifespan would profoundly affect culture and technology development. If an alien species naturally lives for thousands of years, they might approach problems with a patience humans cannot fathom, willing to spend centuries on single projects. Their sense of urgency and change would operate on timescales that would frustrate any human trying to interact with them. Conversely, a species with lifespans of only a few years might compress their entire cultural and technological development into periods that humans would find incomprehensibly rapid. Environmental factors would shape not just biology, but psychology and culture. A species that evolved in oceans might think about space and boundaries very differently than land-dwelling humans. Without solid ground beneath them, without permanent structures that last for generations, their concepts of property, territory, and permanence might be fluid in ways humans struggle to understand. A species that evolved in dense forests with limited sightlines might have very different concepts of distance and perspective than humans who evolved in open savannas, where seeing for miles was possible and valuable. Technology would develop based on available resources and environmental challenges. A civilization on a water world with no dry land would never discover fire, fundamentally altering their technological development pathway. Without fire, they couldn't easily work metals, make pottery, or develop steam power. Their technology might focus on biological engineering, breeding organisms to serve specific functions, or on working with materials that don't require heat processing. They might develop advanced understanding of hydrodynamics, pressure, and acoustic phenomena, while lacking technologies that humans developed early. A civilization on a planet with extreme temperature swings might prioritize insulation and environmental control. A species on a tidally locked planet with one side in permanent daylight and the other in eternal darkness might build their civilization in the twilight zone between extremes. Or they might develop two separate cultures adapted to the radically different environments. Their technology would need to handle these extremes, perhaps leading to advanced materials science long before other fields developed. Reproduction methods would influence family structures and social organization. If aliens reproduce through spawning like fish, releasing eggs and sperm into water where fertilization occurs externally, they might have no concept of nuclear family or parental bonds. Eggs might be raised communally or even left to develop independently. If reproduction requires 3 or more sexes simultaneously, their social structures and mating rituals would be incomprehensibly complex to humans. If they reproduce through budding or fission, creating genetic copies of themselves, their concepts of individuality and identity might be fundamentally different from species that reproduce sexually and value genetic diversity. Sensory experiences beyond human comprehension might exist. Some Earth organisms detect magnetic fields, electric fields, pressure changes, or polarized light, senses humans lack entirely. An alien species might perceive reality through senses we don't possess and cannot easily imagine. They might see the world through echolocation like bats, building a sonic map of their environment. They might sense electrical fields like sharks detecting the bioelectric signatures of other organisms. They might perceive time differently, with reaction times much faster or slower than humans, making their subjective experience of duration incompatible with ours. The Fermi paradox asks why, if alien civilizations are likely to exist, we haven't detected them yet. One possible answer is that we're looking for the wrong things. We search for radio signals because that's how we communicate, and we look for visible structures, like cities, because that's how we build. But an alien civilization might never develop radio technology, using entirely different communication methods. They might build in ways that leave no visible trace from space. They might exist on entirely different timescales, civilizations that rise and fall in centuries, while humans are still learning to farm, or civilizations that operate so slowly that their entire recorded history spans less time than a human lifetime. If contact ever occurs between human and alien civilizations, the challenges would be immense. Even if both species are trying to communicate, fundamental differences in sensory experience, cognition, timescales, and conceptual frameworks might make mutual understanding nearly impossible. Imagine trying to explain color to someone born blind, or music to someone born deaf, or love to a species that doesn't experience emotions. Now multiply those challenges by every aspect of existence: time, space, causation, identity, purpose. Communication might require generations of effort and specialized translation technologies we haven't yet imagined. What alien civilizations might actually look like encompasses possibilities ranging from vaguely familiar, carbon-based organisms breathing oxygen on Earth-like worlds, shaped by convergent evolution into forms somewhat similar to Earth's creatures, to utterly incomprehensible beings whose very existence challenges our definitions of life, intelligence, and civilization. They might be silicon-based entities living in molten rock at temperatures that would vaporize Earth's organisms. They might be electromagnetic patterns in planetary magnetic fields, or chemical reaction networks in liquid methane seas, or quantum coherence patterns in neutron star crusts. The universe is vast and ancient, and if intelligence has emerged elsewhere, it has had billions of years and countless different environments in which to develop into forms limited only by physics, chemistry, and the creative power of evolution operating across deep time on worlds we've never seen. The thick atmospheres of Jupiter and Saturn. Jupiter and Saturn are fundamentally different from the rocky planets of the inner solar system. They have no solid surface to stand on, no ground beneath the sky. Instead, these gas giants are essentially enormous atmospheres all the way down, layers upon layers of gas that gradually transition from thin upper hazes to dense, crushing depths, where pressure transforms hydrogen into states of matter that don't exist naturally anywhere on Earth. Understanding these thick atmospheres means understanding worlds where the atmosphere isn't just a thin shell surrounding a planet, it is the planet. The atmospheres of Jupiter and Saturn are composed primarily of hydrogen and helium, the two lightest and most abundant elements in the universe. Jupiter's atmosphere is about 90% hydrogen and 10% helium by number of molecules, with trace amounts of methane, ammonia, water vapor, and other compounds making up less than 1%. Saturn has a similar composition, though with slightly less helium, about 96% hydrogen and 3% helium, with the missing helium thought to have settled deeper into the planet's interior over billions of years. This composition mirrors the composition of the Sun and the primordial solar nebula from which the planets formed, marking these giants as worlds that captured and retained their original atmospheres from the planet-forming disk. The visible clouds we see when we look at Jupiter and Saturn exist in the uppermost layers of these atmospheres, in a region where temperatures and pressures allow various compounds to condense into droplets and crystals. On Jupiter, the highest cloud layer consists of ammonia ice crystals forming at temperatures around -150 degrees Celsius, where ammonia gas freezes into white ice. These ammonia clouds give Jupiter's zones, the bright bands that circle the planet, their brilliant white appearance. Below this ammonia layer, at slightly higher temperatures and pressures, ammonium hydrosulfide forms another cloud deck, creating brown and tan colours. Deeper still, water ice and liquid water droplets form clouds, though these are rarely visible from above, hidden beneath the overlying layers. Saturn's cloud structure is similar but more subdued. The planet appears more uniformly golden tan because a high-altitude haze of unknown composition partially obscures the underlying cloud layers. This haze may consist of complex organic molecules called tholins, created when ultraviolet light from the sun breaks apart methane molecules in the upper atmosphere, allowing the fragments to recombine into larger, more complex hydrocarbons. These organic hazes absorb blue light and scatter red and yellow light, giving Saturn its characteristic buttery colour. The temperatures in these atmospheres change dramatically with depth. At the cloud tops, where pressure is similar to Earth's atmospheric pressure at sea level, temperatures on Jupiter hover around -145 degrees Celsius. On Saturn, they're even colder, around -180 degrees Celsius, because Saturn is nearly twice as far from the Sun and receives less solar heating. But as you descend into these atmospheres, temperatures rise rapidly. The increase comes partly from the Sun's heat that has been absorbed and transported downward, but more significantly from the planet's internal heat. Both Jupiter and Saturn emit more energy than they receive from the Sun. Jupiter radiates about 1.7 times as much energy as it absorbs from sunlight, while Saturn radiates about 1.8 times as much. This extra energy comes from the planet's interiors. Jupiter is still slowly contracting under its own gravity, a process that converts gravitational potential energy into heat through a mechanism called Kelvin-Helmholtz contraction, named after the physicists Lord Kelvin and Hermann von Helmholtz, who described this process in the 19th century. Saturn has an additional heat source. Helium is slowly separating from hydrogen in its interior and sinking toward the center, releasing gravitational energy as it falls. Much like rain falling through Earth's atmosphere releases energy. This internal heat drives powerful convection in the atmospheres. Warm gas rises from the depths, cools as it rises and expands, then sinks back down to be heated again. This convection creates enormous circulation cells that organize the atmospheres into the distinctive banded patterns visible on both planets. Rising gas forms the bright zones, where fresh ammonia ice crystals condense and create white clouds. Sinking gas forms the darker belts, where descending motion prevents cloud formation and allows us to see deeper into the atmosphere, where darker compounds and higher temperatures exist. The winds on Jupiter and Saturn are among the strongest in the solar system. Jupiter's equatorial region rotates faster than the rest of the planet, with winds reaching speeds of about 360 kilometers per hour, roughly 225 miles per hour. Saturn's equatorial winds are even more extreme, racing along at up to 1,800 kilometers per hour, over 1,100 miles per hour, making them the fastest planetary winds in the solar system. These winds are organized into jet streams, narrow bands of fast-flowing gas that separate the zones and belts. The jet streams are remarkably stable, maintaining their positions and speeds for decades or longer. The Great Red Spot on Jupiter is perhaps the most famous atmospheric feature in the solar system. This enormous storm, large enough to swallow 2 or 3 Earths, has been observed continuously since at least 1830, and possibly as far back as the 1660s, when early telescope observers noted a large spot on Jupiter. The storm is an anticyclone, rotating counterclockwise in Jupiter's southern hemisphere, with winds at its edges reaching 400 kilometers per hour. The storm's longevity remains somewhat mysterious. On Earth, hurricanes dissipate within days or weeks when they move over land or cooler water, but the Great Red Spot has persisted for centuries. Its stability likely comes from the fact that Jupiter has no solid surface to create friction and slow the winds, and the storm may draw energy from the smaller storms it absorbs, and from the temperature difference between the warm interior and cold upper atmosphere. Saturn hosts similar, but generally smaller and shorter-lived storms. Approximately once per Saturnian year, about every 30 Earth years, a massive storm erupts in Saturn's northern hemisphere, growing to encircle the entire planet before eventually dissipating. These great white spots, as they're called, were observed in 1876, 1903, 1933, 1960, 1990, and 2010, following a remarkably regular pattern tied to Saturn's seasons. The storms appear to originate when seasonal heating destabilizes the atmosphere, allowing deep, moist convection to punch through the stable layers above and create violent thunderstorms. Lightning occurs on both Jupiter and Saturn, detected by the Voyager, Galileo, and Cassini spacecraft through radio emissions, and in some cases visible flashes. The lightning on these worlds is similar to terrestrial lightning, electrical discharges between regions of different charge within clouds, but can be far more powerful than Earth's lightning. Individual lightning bolts on Saturn have been measured at up to 1 million times more powerful than typical lightning on Earth. These storms occur in the water cloud layer, where the same process that creates thunderstorms on Earth, rising moist air forming clouds and separating electrical charges, operates on these giant planets. As you descend deeper into these atmospheres, the pressure increases relentlessly. At depths of a few hundred kilometers below the cloud tops, pressures reach thousands of times Earth's atmospheric pressure, and temperatures climb to hundreds of degrees Celsius. The atmosphere becomes denser and denser, transitioning gradually from gas to liquid, though there's no sharp boundary, no ocean surface where you suddenly plunge from air into water. Instead, the hydrogen and helium gradually become so compressed that they take on liquid properties, while still being hot enough that calling them liquid doesn't quite capture their state. They exist in a supercritical fluid state, where the distinction between gas and liquid breaks down. Descend even deeper, to depths of 10,000 to 20,000 kilometers, and pressures reach millions of times Earth's atmospheric pressure. Under these extreme conditions, hydrogen transforms into metallic hydrogen, a state of matter where the atoms are squeezed so tightly that their electrons are freed from individual atoms and flow through the material like electrons in a metal. This metallic hydrogen is thought to make up the bulk of Jupiter's mass and a significant portion of Saturn's. It's an excellent electrical conductor, and the flow of metallic hydrogen in these regions, driven by the planet's rotation and internal convection, generates the powerful magnetic fields that both planets possess. The transition from molecular hydrogen to metallic hydrogen isn't abrupt. There's a gradual change over a range of depths where hydrogen takes on increasingly metallic properties. Scientists study this transition using laboratory experiments that compress hydrogen to extreme pressures and sophisticated computer simulations that model how atoms behave under conditions impossible to fully recreate on Earth. Understanding metallic hydrogen is crucial for understanding the interiors of Jupiter and Saturn, yet its properties remain uncertain because the pressures required, several million times atmospheric pressure, can only be achieved briefly in laboratory settings. At the very centers of Jupiter and Saturn may lie rocky cores, though whether these cores exist and how large they might be remains debated. Jupiter might have a core of rock and ice, containing 10 to 20 Earth masses, or it might have no distinct core at all, just a gradual increase in the concentration of heavy elements toward the center. Saturn might have a similar core, though perhaps smaller relative to the planet's total mass. NASA's Juno mission to Jupiter and the Cassini mission's final orbits, diving between Saturn and its rings, have provided gravity measurements precise enough to constrain the planet's interior structures, revealing that both planets have somewhat diffuse cores rather than sharp boundaries between core and envelope. The scale of these atmospheres is almost incomprehensible. On Earth, the atmosphere extends perhaps 100 kilometers before space begins. On Jupiter and Saturn, the atmosphere extends downward for thousands upon thousands of kilometers, transitioning through states from thin gas to dense supercritical fluid to liquid metallic hydrogen. If you could somehow survive the crushing pressures and searing temperatures and descend through Jupiter's atmosphere, it would take days or weeks of continuous falling to reach the planet's center, passing through layer after layer of hydrogen in different states, all of it technically atmosphere, because there's no solid surface to mark where the atmosphere ends. The study of Jupiter's and Saturn's atmospheres extends beyond academic interest. Understanding how these atmospheres work, how convection organizes into bands, how storms form and persist, how energy is transported from the interior to space, helps scientists understand atmospheric dynamics more broadly. The principles governing Jupiter's atmosphere apply, with appropriate modifications, to Saturn's atmosphere, to the atmospheres of Uranus and Neptune, and even to the atmospheres of giant exoplanets orbiting other stars. Some exoplanets, called hot Jupiters, orbit extremely close to their stars and have atmospheres heated to thousands of degrees, creating extreme versions of the processes we observe on Jupiter and Saturn. These thick atmospheres also serve as laboratories for studying hydrogen under extreme conditions. Most of the normal matter in the universe is hydrogen, and understanding how it behaves under high pressure is crucial for understanding not just giant planets, but also brown dwarfs, objects intermediate in mass between planets and stars, and the interiors of low-mass stars. The hydrogen in Jupiter and Saturn exists across a range of pressures and temperatures that spans from Earth-like conditions in the upper atmosphere to conditions approaching those in stellar interiors in the metallic hydrogen regions, providing natural experiments that inform our understanding of matter itself across a vast range of conditions. The universal laws that would shape all life. While alien life might look nothing like Earth's organisms, using different chemistry, different genetic molecules, different metabolic pathways, certain fundamental principles would constrain and shape all life everywhere in the universe. These universal laws arise not from biological specifics, but from physics, chemistry, thermodynamics, and information theory, disciplines that operate identically throughout the cosmos. Understanding these universal constraints reveals what all life, no matter how alien, must have in common, and what fundamental challenges every living system must solve to exist, grow, reproduce, and evolve on any world, under any star, in any galaxy. The laws of thermodynamics govern all physical processes, and life is no exception. The second law of thermodynamics states that entropy, disorder, tends to increase in closed systems. Left to themselves, organized structures break down, concentrated energy disperses, and order gives way to chaos. A sandcastle erodes, a hot cup of coffee cools to room temperature. Complex molecules break apart into simpler ones. This universal tendency toward disorder creates life's fundamental challenge. Living organisms are highly organized, low-entropy systems existing in a universe that constantly pushes toward disorder. Maintaining biological organization requires constant energy input to fight against entropy's relentless pull. All life, everywhere in the universe, must extract energy from its environment and use that energy to maintain and build ordered structures. On Earth, photosynthetic organisms capture energy from sunlight. Other organisms obtain energy by consuming and metabolizing food, breaking down the chemical bonds in organic molecules and harnessing the released energy. Chemosynthetic organisms extract energy from inorganic chemical reactions. The specific mechanisms vary enormously, but the underlying requirement is universal. Every living thing must have a metabolism, some way of extracting usable energy from its surroundings to power the processes that maintain life. This creates a fundamental constraint. Life can only exist where energy flows. Environments in perfect thermodynamic equilibrium, where no energy gradients exist, cannot support life. Life requires disequilibrium, a hot vent and cold water, sunlight falling on chemical systems, redox gradients between different chemical species. These disequilibria provide the energy flow that life harnesses. Alien life, no matter what chemistry it uses or what planet it inhabits, must exist in regions where energy flows from higher to lower energy states, capturing some of that flowing energy to power metabolism. Evolution through natural selection represents another universal principle. Any system capable of reproduction, variation, and selection will inevitably evolve. This is not a biological principle, but a logical and mathematical necessity. If organisms reproduce, creating copies of themselves, and if those copies are not perfect but contain variations, and if some variants survive and reproduce more successfully than others due to those variations, then the population will change over generations as successful variants become more common and unsuccessful variants decline. This is evolution by natural selection, and it operates on any replicating system with heritable variation subject to selection pressures. Alien life would therefore inevitably evolve, becoming adapted to its environment through countless generations of selection favouring organisms better suited to local conditions. The specific adaptations would differ. Alien organisms might evolve features we've never imagined, but the process would be the same. Evolution is not optional or unique to Earth. It's a fundamental consequence of how replicating systems behave over time. Any civilization that discovers alien life would find that life has been shaped by evolution just as Earth's life has been shaped, even if the resulting organisms look and function completely differently. This evolutionary principle creates a corollary, convergent evolution, where different lineages independently evolve similar solutions to similar problems, occurs because physics and chemistry constrain the possible solutions. Eyes evolved independently many times on Earth because detecting light provides such valuable information, and focusing light onto photosensitive cells is the most effective way to create detailed images. Streamlined body shapes evolved independently in fish, dolphins, ichthyosaurs, and penguins because that shape minimizes drag in water. These convergences occur because physical laws determine what works well in given circumstances. Alien life would show similar convergences. Any organism that needs to move through fluid efficiently would likely evolve some form of streamlined shape because physics demands it. Any organism that needs to detect electromagnetic radiation would likely evolve some structure that captures and focuses that radiation. The details would vary. Alien eyes might have 10 light-sensing structures instead of 2, might sense infrared instead of visible light, might use completely different photosensitive molecules than Earth organisms. But the basic function would be similar because the physics of light detection operates universally. Information storage and transmission represent another universal requirement. Living organisms must store information about how to build and maintain themselves, and they must transmit this information to their offspring. On Earth, this information is stored in DNA and RNA sequences, but the specific molecule doesn't matter. What matters is that some physical system must encode instructions that can be copied and passed to the next generation, and these instructions must contain enough information to specify the organism's structure and function with sufficient detail that offspring resemble parents. The amount of information required sets minimum limits on the complexity of genetic systems. A viable organism cannot be specified by just a few bits of information. It requires substantial information content to encode even the simplest metabolic pathways, structural components, and reproduction mechanisms. Earth's simplest free-living bacteria have genomes containing roughly 500,000 base pairs, encoding about 500 genes. This represents the approximate minimum information content for independent life under Earth conditions. Alien life might require more or less information, depending on environmental complexity and metabolic strategies, but some minimum threshold exists below which organisms cannot encode enough instructions to function and reproduce reliably. The fidelity of information copying, how accurately genetic information is replicated, creates a universal trade-off. Perfect copying with zero errors would prevent evolution because no variation would arise. But too many copying errors would lead to error catastrophe, where genetic information degrades faster than selection can eliminate harmful mutations. There exists an optimal error rate that balances stability and evolvability, allowing organisms to maintain essential functions while still generating the variation necessary for adaptation. Alien genetic systems would face this same trade-off and would likely evolve error rates in a similar optimal range, regardless of what molecules store their genetic information. Physical scaling laws constrain organism size and structure. The strength of materials scales with cross-sectional area, proportional to the square of linear dimensions, while weight scales with volume, proportional to the cube of linear dimensions. This means that, as organisms get larger, their weight increases faster than their structural strength. A human scaled up to 10 times normal height would weigh 1,000 times as much, but would have bones only 100 times as strong. The skeleton would collapse under the weight. This scaling law explains why large land animals have thick, sturdy legs relative to their body size, while small animals have gracile limbs. Elephants have legs like pillars. Mice have delicate, thin legs. An alien planet with higher gravity would have organisms with even thicker, stronger structural supports relative to their size. A lower gravity planet would allow more slender structures. But the mathematics of scaling operates universally, constraining what body plans are physically possible at different sizes. Surface area to volume ratio creates another universal constraint. Small organisms have large surface area relative to their volume, making heat loss rapid and making diffusion effective for transporting materials. Large organisms have small surface area relative to volume, retaining heat more effectively but requiring specialized circulatory systems because diffusion becomes inadequate for transporting nutrients and waste across large distances. These scaling relationships would govern alien life just as they govern Earth life, determining which transport mechanisms are necessary at different sizes and what thermal regulation strategies are required. Chemical reaction rates depend on temperature, creating universal constraints on metabolism. Higher temperatures speed up chemical reactions exponentially. A rule of thumb is that reactions roughly double in rate for every 10-degree increase in temperature. This means organisms in hot environments can have faster metabolisms, grow more quickly, and potentially think faster if they're intelligent. Organisms in cold environments have slower metabolisms, grow more slowly, and would process information more slowly if conscious. These temperature effects on reaction kinetics are universal, affecting any chemistry-based life, regardless of specific biochemistry. Diffusion rates determined by physics limit how large cells can be. Molecules move through cells by random thermal motion, diffusion. This process is slow. A molecule might take seconds or minutes to diffuse across a large cell. This limits cell size because cells need to move nutrients, wastes, and signals around internally, and diffusion becomes prohibitively slow beyond certain sizes. Earth's largest cells are only about 1 millimeter across, and most are much smaller. Alien cells, regardless of their chemistry, would face similar diffusion limits unless they evolved active transport mechanisms, like Earth's eukaryotic cells use, with molecular motors moving cargo along cellular highways. The speed of light creates absolute limits on information transfer. No signal can travel faster than light, which means there are minimum response times for any organism based on its size. An organism the size of a bacterium, a few micrometers, experiences internal light travel times of trillionths of a second, essentially instantaneous. But a hypothetical, planet-sized organism would experience light travel times of tens of milliseconds from one side to the other, creating unavoidable delays in communication and coordination between distant parts. Very large organisms would necessarily be slow to respond to stimuli and might need decentralized control systems because centralized coordination becomes impractical when signal delays become significant. Energy efficiency sets ultimate limits on what metabolic processes are possible. Chemical reactions have maximum energy yields determined by the bonds being broken and formed. An organism cannot extract more energy from a reaction than the chemistry allows. This means life on worlds with limited energy availability, dim stars, deep subsurface environments, chemical poor conditions would necessarily have low energy lifestyles, growing slowly and reproducing infrequently. High energy environments allow active, energetic lifestyles, but also demand mechanisms to dissipate excess heat. Water's unique properties, while not absolutely required for life, make it an excellent solvent for biochemistry. Water remains liquid across a convenient temperature range, has high heat capacity that buffers against temperature changes, expands when freezing so ice floats, acts as a polar solvent that dissolves ions and many organic molecules, and participates in many biochemical reactions. While life could potentially use other solvents, liquid ammonia, methane, supercritical carbon dioxide, any solvent must have properties that allow complex chemistry to occur, molecules to dissolve and interact, and cellular compartments to form. Not many liquids have the right combination of properties, making water-based life probably more common than exotic alternatives, though not exclusively so. Complexity emerges hierarchically, with simple components combining into more complex structures, which combine into still more complex systems. Atoms form molecules. Molecules form macromolecules. Macromolecules form cellular structures. Cells form tissues. Tissues form organs. Organs form organisms. Organisms form ecosystems. This hierarchical organization seems to be how complexity arises universally, because building complex systems directly from simple components becomes unmanageable beyond certain complexity levels. Modular hierarchical construction allows greater complexity to be achieved and maintained. Alien life would likely show similar hierarchical organization, even if the specific components at each level differ completely from Earth's biological hierarchy. Darwinian selection favors efficiency. Organisms that use resources more efficiently have advantages over wasteful competitors. This drives evolution toward optimized solutions within physical constraints. Alien life would similarly be shaped by selection for efficiency, though what constitutes efficient depends on environmental context. In energy-rich environments, speed might matter more than efficiency. In energy-poor environments, extreme efficiency becomes essential for survival. But the general principle that natural selection tends to optimize organisms for their specific circumstances within physical constraints operates universally. The universal laws that would shape all life encompass thermodynamics, demanding that life exist only where energy flows, and that organisms extract energy to maintain order against entropy. Evolution, through natural selection, being an inevitable consequence of imperfect replication with variation. Information requirements, setting minimum complexity thresholds, scaling laws constraining size and structure, chemical kinetics determining metabolic rates, and physical limits on signal speeds, and diffusion rates imposing fundamental constraints on how large and fast organisms can be. These laws operate identically throughout the universe, guaranteeing that while alien life might look and function completely differently from Earth's organisms in countless details, the fundamental principles governing life's existence, evolution, and physical limitations would be the same everywhere, creating a common framework that all life must operate within, regardless of whether it's based on carbon or silicon, DNA or something entirely different, oxygen metabolism or sulfur chemistry. Because physics and chemistry and thermodynamics and information theory operate identically on every world orbiting every star in every galaxy, creating universal constraints that shape all possible forms of life into entities that must harvest energy, maintain organization, store and transmit information, and evolve through selection, making these principles the true universals of biology that would apply to any living thing humans might ever encounter. The incredible density of neutron stars. Imagine taking the entire mass of our Sun, a sphere so large that over 1 million Earths could fit inside it, and compressing it down to the size of a city. Not a large metropolitan area, sprawling across thousands of square miles, but just the central core, perhaps 12 or 15 miles across. This is a neutron star, an object so dense that a single teaspoonful of its material would weigh about 1 billion tons on Earth. To put that in perspective, that single teaspoon would weigh more than all the cars, trucks and buildings in a major city combined. This density is so extreme that it represents a fundamentally different state of matter, one that can only exist under the most extraordinary conditions in the universe. Neutron stars are born in the violent death throes of massive stars. When a star much larger than our Sun, typically at least 8 times more massive, exhausts the nuclear fuel in its core, it can no longer generate the heat and pressure needed to support itself against its own gravity. The core collapses catastrophically in less than a second, falling inward at speeds approaching 1/4 of the speed of light. The outer layers of the star, rebounding from this collapse, are blown away in a supernova explosion that briefly outshines an entire galaxy. What remains at the center, crushed under its own gravity to densities that boggle the mind, is a neutron star. To understand how neutron stars achieve such incredible density, you need to understand what happens to matter under extreme compression. In normal matter, atoms are mostly empty space. The nucleus of an atom containing protons and neutrons occupies only a tiny fraction of the atom's volume. The rest is empty space with a few electrons orbiting at relatively vast distances. In a solid object, like a piece of iron or a rock, the atoms are packed as closely together as the electromagnetic forces between them allow, but there's still enormous amounts of empty space within each atom. As you compress matter to higher and higher densities, you eventually overcome the forces that keep atoms intact. The electrons are stripped away from their nuclei, creating a plasma of free electrons and atomic nuclei. Compress further, and the electrons themselves are forced to occupy higher and higher energy states due to quantum mechanical principles. Eventually, at densities found in white dwarf stars, electron degeneracy pressure provides the support against gravity. The electrons can't be compressed any further without violating the Pauli exclusion principle, which forbids identical particles from occupying the same quantum state. But if you compress matter beyond even this point, as happens in the core collapse of a massive star, something remarkable occurs. The electrons are forced so close to the protons in atomic nuclei that they combine through a process called electron capture. A proton and an electron merge to form a neutron, releasing a neutrino in the process. This happens not just occasionally, but to nearly every proton in the collapsing core. Within a fraction of a second, the matter that was once composed of atoms, with protons, neutrons and electrons maintaining their separate identities, transforms into a sea of neutrons, packed together so tightly that they're essentially touching. The neutrons themselves now provide the pressure that supports the star against further collapse. Just like electrons, neutrons obey the Pauli exclusion principle and cannot be compressed indefinitely. This neutron degeneracy pressure halts the collapse, but only after the matter has been compressed to densities comparable to that of an atomic nucleus. In fact, you can think of a neutron star as essentially a single gigantic atomic nucleus, several kilometers across, containing more neutrons than there are atoms in all the planets of our solar system combined. The density at the center of a neutron star is estimated to be around 500 million to perhaps 1 billion tons per cubic centimeter. At these densities, a cubic centimetre, about the size of a sugar cube, would contain more mass than Mount Everest. The entire mass of humanity, every person on Earth, could be compressed into a volume smaller than a grain of sand at neutron star densities. These numbers are so far beyond everyday experience that they almost lose meaning, but they represent real physical conditions that exist in these objects. The structure of a neutron star is complex and layered. At the surface, there's a thin atmosphere only a few centimeters thick, composed of hydrogen, helium, or heavier elements, depending on the star's history. Below this lies the outer crust, where matter exists in a crystalline lattice. Here, atomic nuclei, now incredibly neutron-rich and unlike any nuclei found on Earth, are arranged in a solid structure with a sea of electrons moving between them. This crust is extraordinarily rigid. It's been calculated that the material of a neutron star's crust is about 10 billion times stronger than steel. Deeper into the neutron star, at densities about 1,000,000 times that of normal atomic nuclei, the inner crust begins. Here, neutrons start to leak out of the nuclei and form a superfluid that exists between and around the nuclei. A superfluid is a state of matter with zero viscosity. It flows without any resistance whatsoever. This neutron superfluid can exhibit bizarre quantum mechanical behavior on a macroscopic scale. Below the crust lies the outer core, where the density becomes so high that nuclei dissolve entirely into a uniform liquid of neutrons, with a small admixture of protons and electrons to maintain charge neutrality. The neutrons in this region form a superfluid, while the protons form a superconductor, a state where electrical current can flow without resistance. These quantum fluids make up the bulk of the neutron star's interior. At the very centre, in the inner core, conditions become so extreme that we're not entirely certain what happens. The density may exceed that of atomic nuclei by a factor of several times. At these densities, neutrons themselves might break down into their constituent quarks, creating what's called a quark-gluon plasma, or strange quark matter. Alternatively, other exotic particles, predicted by physics but never observed, might appear. The centre of a neutron star is one of the few places in the universe where matter exists in states that can't be recreated or studied in laboratories on Earth. The incredible density of neutron stars creates gravitational fields so strong that they noticeably warp space-time. At the surface of a neutron star, gravity is about 200 billion times stronger than on Earth. If you could somehow stand on a neutron star's surface, though you would instantly be crushed and vaporized, you would weigh 200 billion times more than you do on Earth. A fall from even a tiny height of 1 centimetre would be fatal, as you would hit the surface at a significant fraction of the speed of light. This intense gravity affects light itself. Photons climbing out of a neutron star's gravitational well lose energy through gravitational redshift. Light that starts as high-energy X-rays at the surface might emerge as lower-energy radiation by the time it escapes into space. The gravity also bends light rays, causing light from the far side of the neutron star to curve around and become visible to an observer. This means you could potentially see more than half of the neutron star's surface at once, as light from behind the star bends around it to reach your eyes. The intense gravity also means that space and time are severely warped near a neutron star. Clocks at the surface of a neutron star run about 30% slower than clocks far away in flat space-time. This time dilation is a real physical effect. Processes genuinely occur more slowly in the strong gravitational field at the surface compared to regions far from the star. The rotation of neutron stars adds another layer of extremes to their already extreme nature. Many neutron stars spin rapidly, some completing hundreds of rotations per second. This happens because of conservation of angular momentum. When the core of the parent star collapses, any rotation it had is amplified enormously as the radius shrinks. Just as a figure skater spins faster When pulling their arms in, a collapsing stellar core spins faster as it shrinks. The result can be a neutron star spinning so fast that its equator is moving at a significant fraction of the speed of light. The fastest spinning neutron star known rotates 716 times per second. Imagine an object with more mass than the Sun, compressed to the size of a city, spinning around more than 700 times every second. The surface at the equator of this neutron star is moving at about 24% of the speed of light. At these rotation rates, centrifugal forces become significant, causing the neutron star to bulge at the equator and flatten at the poles. Yet even with this rapid rotation and the outward force it creates, the neutron star holds together, a testament to the incredible strength of neutron degenerate matter and the overwhelming power of its gravity. The magnetic fields of neutron stars are among the strongest in the universe. The collapse that forms a neutron star compresses and amplifies any magnetic field present in the parent star's core. The result can be magnetic fields 1 trillion times stronger than Earth's magnetic field. Some neutron stars, called magnetars, have fields even stronger, up to 1,000 times more intense still. At these field strengths, quantum mechanical effects become important. The vacuum of space itself becomes polarized by the magnetic field, affecting how light propagates. Atoms stretched by these fields become elongated, many times longer than they are wide, fundamentally changing their properties. These magnetic fields, combined with rapid rotation, power some of the most energetic phenomena in the universe. Charged particles, accelerated along magnetic field lines, emit beams of radiation from the magnetic poles. If these beams sweep across Earth as the neutron star rotates, we detect regular pulses of radiation, which is why many neutron stars are called pulsars. The precision of these pulses rivals that of atomic clocks, with some pulsars maintaining their timing to within microseconds over years or decades. The density of neutron stars also means that they have very deep gravitational wells. The escape velocity from the surface of a typical neutron star is about 150,000 kilometers per second, roughly half the speed of light. This means that matter falling onto a neutron star from a companion star in a binary system releases tremendous amounts of energy. The infalling material accelerates to these extreme velocities and slams into the surface with incredible force, heating to temperatures of hundreds of millions of degrees and emitting intense X-rays and gamma rays. Neutron stars can also collide with each other in binary systems where two neutron stars spiral together due to the emission of gravitational waves. When they finally merge, the collision creates conditions even more extreme than those in individual neutron stars. The merger produces a burst of gravitational waves that ripple through space-time, along with electromagnetic radiation across the spectrum. These collisions are thought to be the primary source of heavy elements like gold and platinum in the universe, forged in the incredibly dense, hot material ejected during the merger. The study of neutron stars provides a unique laboratory for physics under extreme conditions. The densities, magnetic fields, rotation rates, and gravitational fields found in and around neutron stars simply don't exist anywhere else that we can observe. By studying these objects, physicists can test theories about how matter behaves at nuclear densities, how gravity warps spacetime in strong field regimes, and how quantum mechanics manifests on macroscopic scales. Every observation of a neutron star, every measurement of its mass, radius, rotation, or cooling rate provides constraints on fundamental physics that cannot be obtained any other way, offering glimpses into realms of matter and energy that push the very boundaries of our understanding. The solar wind that flows through space. From the surface of the Sun, an invisible river flows outward in all directions, streaming past the planets and extending far beyond the orbit of Pluto into the distant reaches of the solar system. This is the solar wind, a continuous flow of charged particles, primarily electrons and protons, that escape from the Sun's outer atmosphere and race through space at speeds ranging from 250 to over 500 miles per second. This wind carries with it pieces of the Sun itself, along with magnetic fields that thread through the solar system, creating an enormous bubble of solar influence that shapes the space environment around every planet. The story of the solar wind begins in the Sun's corona, the outermost layer of the solar atmosphere that extends millions of miles above the visible surface. The corona is paradoxically much hotter than the surface below it, while the Sun's visible surface, the photosphere, has a temperature of about 10,000 degrees Fahrenheit. The corona reaches temperatures exceeding 2 million degrees. This extreme heating, still not completely understood, but likely involving magnetic fields and wave energy, gives particles in the corona so much energy that many of them move faster than the Sun's escape velocity. Imagine standing at the Sun's surface and throwing a baseball upward. To escape the Sun's gravity, you would need to throw it at about 380 miles per second. In the corona, thermal energy heats particles to such extreme temperatures that a significant fraction of them are moving faster than this escape velocity. These particles don't fall back to the Sun. They stream away into space, carrying energy and momentum with them. The Sun is essentially evaporating, losing mass continuously through this process, though at a rate so slow that it would take trillions of years to evaporate completely. The solar wind is not uniform. It flows faster from some regions of the Sun than others, creating a complex structure as it expands outward. Above the Sun's equatorial regions, where magnetic field lines tend to loop back to the surface, the solar wind emerges more slowly, typically around 250 miles per second. But at the Sun's poles and in coronal holes, regions where magnetic field lines extend far into space, rather than looping back, the wind flows much faster, reaching speeds of 500 miles per second or more. These variations in speed create interaction regions where fast solar wind catches up to slow solar wind. Imagine cars on a highway where fast-moving traffic overtakes slower-moving traffic. The fast solar wind compresses the slow solar wind ahead of it, creating regions of enhanced density and magnetic field strength. These co-rotating interaction regions, named because they rotate with the Sun as it spins, sweep through the solar system like a spiral pattern, buffeting planets with alternating streams of slow and fast wind. As the solar wind flows outward, it carries the Sun's magnetic field with it. The magnetic field lines become stretched and twisted, creating a spiral pattern much like water from a rotating garden sprinkler. This interplanetary magnetic field threads through the entire solar system, connecting magnetically active regions on the Sun to the distant reaches of space. When magnetic field lines from different regions of the Sun come together, in space they can reconnect, releasing energy and accelerating particles to even higher speeds. The solar wind is not just a steady breeze but includes violent gusts and storms. When an eruption occurs on the Sun, a solar flare or a coronal mass ejection, enormous quantities of plasma and magnetic field can be hurled into space far faster than the normal solar wind. A coronal mass ejection can contain billions of tons of material moving at speeds up to several thousand miles per second. When one of these structures reaches Earth, typically 1 to 3 days after leaving the Sun, it can compress Earth's magnetic field, trigger spectacular auroras, and potentially disrupt satellites, power grids, and communication systems. The journey of a solar wind particle from the Sun to Earth takes about 4 to 5 days travelling at typical speeds. During this journey, the particle encounters very little. Space between the Sun and Earth is remarkably empty. A cubic inch of the solar wind near Earth contains only about 5 to 10 protons, far more tenuous than even the best vacuum we can create in laboratories on Earth. Yet despite this extreme sparseness, the solar wind carries significant momentum and energy simply because of the vast volume through which it flows and the speeds at which it travels. When the solar wind encounters a planet, what happens depends on whether that planet has a magnetic field. Earth's magnetic field creates a protective bubble called the magnetosphere that deflects most of the solar wind around the planet. The interaction is dynamic and complex. The leading edge of Earth's magnetosphere, called the bow shock, is where the supersonic solar wind first encounters Earth's magnetic field and slows down abruptly, much like air piling up in front of a supersonic aircraft creates a shock wave. This shock heats the solar wind and diverts it around Earth's magnetosphere, creating a turbulent boundary layer called the magnetosheath. Some solar wind particles do manage to penetrate into Earth's magnetosphere, particularly when reconnection occurs between the interplanetary magnetic field and Earth's magnetic field. These particles get funneled along Earth's magnetic field lines toward the polar regions, where they collide with atoms in the upper atmosphere, creating the shimmering curtains of light we call auroras. The green and red colours come from oxygen atoms at different altitudes being excited by these collisions, while nitrogen produces blue and purple hues. Planets without magnetic fields like Mars and Venus experience the solar wind very differently. Without a protective magnetic bubble, the solar wind interacts directly with the upper atmosphere. Over millions of years, this interaction strips away atmospheric particles, carrying them off into space. Mars, which once had a thicker atmosphere and possibly liquid water on its surface, has lost much of its atmosphere to this process. The solar wind literally peels away the outer layers of the Martian atmosphere, particularly during strong solar storms, gradually transforming Mars from a potentially habitable world to the thin, dry atmosphere we observe today. The Moon, with neither atmosphere nor magnetic field, receives the full force of the solar wind directly on its surface. Solar wind particles impact the lunar regolith, becoming implanted in the soil. Over billions of years, this process has altered the chemistry and appearance of the lunar surface, darkening it and creating what scientists call space weathering. Ancient lunar rocks brought back by Apollo astronauts contain trapped solar wind particles that serve as a record of how the Sun's output has changed over time. Giant planets like Jupiter and Saturn have enormous magnetospheres that extend millions of miles into space. Jupiter's magnetosphere is so large that if we could see it from Earth, it would appear several times larger than the full moon in the sky. The solar wind compresses these magnetospheres on the side facing the Sun and stretches them into long tails on the night side. Within these giant magnetospheres, the interaction between the solar wind, the planet's magnetic field, and particles from the planet's moons creates some of the most intense radiation environments in the solar system. The solar wind doesn't flow forever. Far from the Sun, billions of miles beyond the orbits of the planets, it begins to slow down as it encounters the interstellar medium, the dilute gas and plasma that fills the space between stars. The Voyager spacecraft, launched in 1977, have travelled far enough to cross the boundary where the solar wind slows to subsonic speeds, called the termination shock. This boundary is not spherical, but is pushed outward in the direction the solar system is moving through the galaxy and compressed in the opposite direction. Beyond the termination shock lies a region called the heliosheath, where the solar wind has slowed but still moves outward, compressed and heated by its interaction with the interstellar medium. The exact shape and extent of this region depend on the strength of the solar wind and the pressure of the interstellar medium outside. Voyager 1 and Voyager 2 have now crossed even farther, passing through the heliopause, the outer boundary where the solar wind effectively stops and interstellar space begins. They are now in a region where the dominant flow is no longer from the Sun, but from the galaxy itself. The structure created by the solar wind, this vast bubble of solar influence, extending billions of miles in all directions, is called the heliosphere. It serves as a partial shield, deflecting some of the cosmic rays that stream through the galaxy. Without this protection, the flux of high-energy particles reaching the inner solar system would be higher, potentially affecting planetary atmospheres and creating more radiation hazards for any life on planetary surfaces. The solar wind varies with the sun's activity cycle. During solar maximum, when the sun is most active with many sunspots and frequent eruptions, the solar wind is stronger, more variable, and more likely to include fast-moving coronal mass ejections. During solar minimum, when the sun is quieter, the wind becomes more regular, though still continuous. This 11-year cycle affects space weather throughout the solar system, influencing everything from auroral activity on Earth to the radiation environment encountered by spacecraft. The composition of the solar wind provides a sample of the sun's outer layers. While predominantly hydrogen, both protons and electrons, the wind also contains helium, making up about 4% of the particles, along with trace amounts of heavier elements, like carbon, nitrogen, oxygen, neon, magnesium, silicon, and iron. These heavier elements are present in much smaller quantities but provide valuable information about solar composition and the processes occurring in the corona. Different types of solar wind have different characteristics. The slow solar wind is denser and cooler, while the fast wind is more tenuous but carries more kinetic energy due to its higher speed. Transient events like coronal mass ejections create temporary structures in the solar wind with dramatically enhanced density, speed, and magnetic field strength. These variations create a constantly changing space environment that spacecraft and planets must navigate. The solar wind also carries information outward from the sun. Disturbances created by solar activity propagate through the solar wind, and by observing how these disturbances evolve and interact as they move through space, scientists can learn about the properties of the wind itself and the magnetic fields threading through it. Spacecraft throughout the solar system serve as sentinels, measuring the solar wind's properties at different locations and providing a three-dimensional view of how this invisible river flows through our cosmic neighborhood. Every star produces a stellar wind, analogous to our solar wind, and these winds play important roles in stellar evolution and in shaping the environments around other planetary systems. Hot, massive stars produce fierce stellar winds that can carry away significant fractions of the star's mass over its lifetime. Cool, evolved stars like red giants produce slower but denser winds. Understanding our own solar wind provides insights into these stellar winds throughout the galaxy, connecting the processes occurring in our immediate space environment to the broader evolution of stars and planetary systems across the universe. What alien oceans might contain? Earth's oceans are vast, salty bodies of liquid water covering more than 70% of the planet's surface, containing dissolved minerals, organic molecules, and a staggering diversity of life, from microscopic bacteria to the largest animals that have ever existed. But oceans on other worlds might be fundamentally different, not just in what organisms inhabit them, but in their very composition. What liquids fill them, what chemicals dissolve in those liquids, and what physical conditions prevail at their depths. Understanding what alien oceans might contain means considering not only water-based oceans with different chemistry than Earth's seas, but entirely different liquids that could serve as oceanic solvents on worlds with radically different temperatures, pressures, and geological histories. The most familiar alien oceans would be water-based oceans on other worlds. Several candidates exist in our own solar system. Europa, Jupiter's ice-covered moon, harbours a global ocean containing perhaps twice as much liquid water as all of Earth's oceans combined, kept liquid by tidal heating from Jupiter's gravity despite surface temperatures around -160 degrees Celsius. This ocean lies beneath an ice shell estimated to be 15 to 25 kilometers thick, shielding the water from the vacuum of space and from Jupiter's intense radiation belts. What Europa's ocean contains remains unknown, but scientific models and the limited data from spacecraft flybys provide clues. The ocean is certainly salty, likely containing dissolved salts leached from Europa's rocky seafloor over billions of years. Magnesium sulfate, sodium chloride, and other salts detected spectroscopically in Europa's ice shell probably came from the ocean below. The salinity might be similar to Earth's oceans, or it might be substantially higher, creating a briny sea where salt concentrations affect water's freezing point, density, and chemistry. High salinity would influence what kinds of life could potentially evolve, favouring organisms with mechanisms to cope with osmotic stress. The ocean would be dark. Absolutely no sunlight penetrates through kilometres of ice. Any life in Europa's ocean would depend on chemical energy rather than photosynthesis. The rocky seafloor might host hydrothermal vents similar to those on Earth's ocean floor, where hot, mineral-rich water spews from cracks in the rock, driven by volcanic heat from the moon's interior. These vents could provide energy and nutrients to support chemosynthetic bacteria that extract energy from chemicals in the vent fluids: hydrogen, methane, hydrogen sulfide, iron compounds. If such microbes exist, they might form the base of a food chain, supporting more complex organisms analogous to the tube worms, clams, and crustaceans that cluster around Earth's hydrothermal vents. Dissolved gases would be present in Europa's ocean: carbon dioxide from reactions between water and rock, hydrogen from water-rock reactions, and possibly from radiolysis, where radiation breaks apart water molecules near the ice-ocean boundary, methane from geological processes, or potentially from biological activity. The concentrations and ratios of these gases would reveal much about the ocean's chemistry and whether biological processes might be occurring. Organic molecules, carbon-based compounds, almost certainly exist in Europa's ocean. Comets and meteorites containing organic compounds have bombarded Europa throughout its history. Chemical reactions between water and rock produce simple organic molecules. If life exists, it would produce far more complex organic molecules: amino acids, lipids, sugars, proteins. Detecting complex organic molecules in samples from Europa's ocean would be strong evidence for biology, though distinguishing biological from non-biological organic chemistry would require careful analysis. Enceladus, Saturn's small moon, provides an even more accessible alien ocean because it actively vents ocean water into space through cracks in its south polar ice shell. The Cassini spacecraft flew through these plumes, analysing their composition directly. The plumes contain water vapour, ice grains, carbon dioxide, methane, ammonia, molecular hydrogen, and complex organic molecules, including some with chains of carbon atoms, ingredients that on Earth would suggest habitability. The presence of molecular hydrogen is particularly intriguing because it suggests water-rock reactions at high temperatures, consistent with hydrothermal vents on Enceladus's seafloor. The organic molecules, while not proof of life, show that organic chemistry is occurring in Enceladus's ocean. Titan, Saturn's largest moon, presents an entirely different type of ocean, not water, but liquid hydrocarbons. Titan's surface temperature hovers around -180 degrees Celsius, far too cold for liquid water, which is frozen as hard as rock. But at these temperatures, methane and ethane exist as liquids. Titan has lakes and seas of liquid hydrocarbons near its poles, bodies of liquid methane and ethane with dissolved propane, butane, nitrogen, and traces of more complex organic molecules. These hydrocarbon seas are hundreds of meters deep in some places, creating environments completely unlike anything on Earth. What Titan's hydrocarbon oceans might contain depends on what chemistry can occur in liquid methane at cryogenic temperatures. Organic chemistry certainly happens. Titan's atmosphere produces complex organic molecules through photochemistry, and these molecules rain down onto the surface, accumulating in the lakes and seas. Nitrogen compounds, cyclic molecules, long-chain hydrocarbons, and possibly even more complex molecules might dissolve in the methane. Whether life could exist in liquid methane remains highly speculative, but if it does, it would use completely different biochemistry than Earth life, perhaps with cell membranes made from molecules that are insoluble in hydrocarbons rather than the water-soluble membranes Earth organisms use. Titan also likely has a subsurface water ocean beneath its icy crust, similar to Europa and Enceladus. This buried ocean would be separate from the surface hydrocarbon seas, creating the possibility that Titan might host two completely different types of chemistry: water-based chemistry in the deep subsurface ocean and hydrocarbon-based chemistry in the surface seas. Whether these two environments could both support life, and whether life in one could be related to life in the other, represents one of the most intriguing questions about this remarkable moon. Ammonia oceans represent another possibility for alien seas. Ammonia remains liquid at temperatures between -77 and -33 degrees Celsius at Earth atmospheric pressure, colder than water but warmer than methane. A planet or moon with temperatures in this range might have oceans of liquid ammonia or ammonia-water mixtures. Pure ammonia is a less effective solvent than water for many compounds, but it can dissolve different substances than water, creating entirely different ocean chemistry. An ammonia ocean would be less dense than water ice, so ammonia ice would sink rather than float, potentially affecting planetary heat transport and ocean circulation. The ocean's pH would be highly alkaline. Ammonia is a base, creating chemistry very different from Earth's near-neutral oceans. Organisms adapted to ammonia oceans would need biochemistry that functions at low temperatures and high pH, potentially using ammonia molecules in ways analogous to how Earth life uses water. Sulfuric acid oceans sound implausible, yet Venus's clouds contain concentrated sulfuric acid droplets, and some scientists have speculated about life existing in these droplets. While Venus's surface is hellishly hot, the cloud layers at altitudes of 50 to 60 kilometers above the surface have temperatures around room temperature, quite comfortable by terrestrial standards. If life could exist as airborne organisms living in cloud droplets, those droplets would be concentrated sulfuric acid, requiring biochemistry completely unlike anything on Earth. Certain Earth microbes can tolerate extremely acidic conditions, proving that acid-resistant biochemistry is possible. But whether life could actually live in sulfuric acid remains unknown and highly controversial. Silicate oceans, molten rock, might exist on lava worlds orbiting extremely close to their stars. At temperatures exceeding 2000 degrees Celsius, rock melts into liquid magma that flows like water. While most scientists consider molten rock too hot and destructive for any conceivable biochemistry, some speculative theories propose exotic life forms based on completely different chemistry that might exist in magma, perhaps using silicate molecules or metal compounds as structural materials instead of carbon-based organic molecules. Such life would be so alien that we might not recognize it as life, even if we observed it directly. Supercritical oceans exist under conditions where temperature and pressure are high enough that the distinction between liquid and gas breaks down. Supercritical water, existing at temperatures above 374 degrees Celsius and pressures above 220 atmospheres, has properties intermediate between liquid and gas. Deep beneath the surfaces of massive ocean worlds, pressures might be high enough to create supercritical water oceans. The chemistry in supercritical water differs dramatically from normal water chemistry, with different solubilities, reaction rates, and molecular interactions. Whether life could adapt to supercritical conditions remains unknown, but the possibility can't be ruled out for extremely exotic organisms. The ocean floor composition profoundly affects ocean chemistry. Earth's ocean floors are basaltic rock, and water-rock interactions continuously cycle elements between the ocean and the crust. Alien ocean floors might be different, perhaps pure ice if the ocean is deep enough that high-pressure ice forms at the bottom, or perhaps carbonate rocks, serpentinite, or other minerals depending on the planet's composition. These different minerals would leach different elements into the ocean, creating different dissolved chemistry. Hydrothermal vents on alien seafloors might vent fluids with very different composition than Earth's vents. On Europa or Enceladus, where the rocky interiors might be rich in different minerals than Earth's mantle, vent fluids might contain unusual concentrations of metals, sulfur compounds, or other chemicals. These different chemistries would favour different types of chemosynthetic organisms if life exists, potentially creating ecosystems with no analogue on Earth. Dissolved oxygen would be rare or absent in most alien oceans unless photosynthetic life has evolved and produced oxygen for billions of years as on Earth. Most alien oceans would be anoxic, without dissolved oxygen, more similar to Earth's oceans before the Great Oxidation Event 2.5 billion years ago. Anoxic oceans contain different dissolved metals and have different chemistry than oxygenated oceans. Iron remains dissolved in anoxic water instead of precipitating as rust. Sulfur chemistry dominates, rather than oxygen chemistry. Life in anoxic alien oceans would use anaerobic metabolism, extracting energy from reactions that don't involve oxygen. Temperature gradients in alien oceans depend on heat sources. Earth's oceans are heated from above by sunlight and from below by geothermal heat, creating complex circulation patterns. Europa's ocean, heated only from below by tidal heating and with a cold ice ceiling above, might have upside-down circulation compared to Earth. Warm water rising from the seafloor toward the ice ceiling where it cools and sinks back down. These circulation patterns would affect nutrient distribution, temperature zones, and where life might be most abundant. Pressure increases with depth in any ocean, but the rate depends on the liquid's density and the world's gravity. Europa's ocean might reach pressures exceeding 10,000 atmospheres at the seafloor, much higher than Earth's deepest ocean trenches, due to the ocean's great depth. Organisms adapted to such extreme pressure would have specialized biochemistry that functions under conditions where molecules are compressed and reaction rates are altered by pressure's effects on molecular structure. Seasonal variations might affect some alien oceans. A planet with significant axial tilt would experience seasonal changes in star heating that could affect surface ocean temperatures, causing seasonal mixing, ice formation and melting, and biological cycles tied to seasons. Tidally locked planets would have no seasonal variations, but might have temperature zones related to distance from the substellar point, the location where the star is directly overhead, creating warm equatorial regions and cold polar regions with different ocean chemistry in each zone. Ice-covered oceans might have ecosystems concentrated near the ice-water boundary, where any photosynthesis using radiation penetrating through cracks in the ice could occur, or where chemical gradients between the ice and deep ocean creates energy harvesting opportunities. Life might cluster in cracks and crevices in the ice ceiling, or in regions where the ice is thinnest and most likely to crack or melt. What alien oceans might contain ranges from the familiar, salty water with dissolved minerals and potentially abundant life, to the exotic, liquid methane seas with dissolved organic compounds, ammonia oceans at cryogenic temperatures, supercritical fluids blurring the line between liquid and gas, even molten silicate magmas on scorching hot worlds. Each ocean's composition reflects its world's temperature, pressure, geology, and history, creating environments where chemistry operates under different rules, where life, if it exists, would be adapted to conditions we can barely imagine, where exploration by future spacecraft might reveal ecosystems as diverse and wondrous as Earth's oceans, or so alien that we struggle to recognize biology when we see it, expanding the inventory of habitable environments to include not just Earth-like water oceans, but any stable liquid where dissolved chemicals, energy sources, and sufficient time might allow chemistry to evolve into biology beneath the waves of alien seas scattered across the solar system and beyond.